Hello everyone, I'm Xiaoming Zhang from Hebei University of Technology. Today, I want to talk about the physical properties and materialization of topological electronic materials. My talk mainly contains these 3 points. First, I will make a brief introduction to the topological materials. Then I will introduce our work on the design of topological materials, and this part contains two parts, which conclude some nodal semimetals in non-magnetic systems, and also some examples of magnetic topological materials. I think we are the most curious on this question: what's the topology? In fact, the topic of topology is firstly appeared in the geometry, namely topological geometry. In the topological geometry, the shape of the buckle and the cup is the same. Yeah, it's sure very interesting. Then, how to define the difference of the topological elements in topological geometry? In fact, it's very simple. We can count the number of holes in the system. Please see this picture. In this picture, there are several examples. We can find there are several examples for the 0 holes, and these 0 hole one are the same, and others have 1 hole, and some have 2 holes, and the 1 hole are the same, and the example for the 2 holes is the same. So in the topological geometry, we can define different topological elements by only counting the number of the holes. Then, how the topological material, appear in the physics is relied in the Hall effect, as shown in this figure. In the electrical conductance, there appears several steps, and they can correspond to the 0 hole, 1 hole, 2 holes, 3 holes, and so on. So this is also topological. So this is the introduction from the topological geometry to the topological physics. This is the history for the topological materials. The topological material can be firstly traced back to the for the 1918. That's the appearance of the quantum Hall effect. Then a model is built by the Holden and for the topological quantum Hall effect. In 2004, the graphene is realized and which promotes the proposal of the quantum spin Hall effect. Then later, in the 2007, the quantum spin Hall effect has been realized in the experiments. Then later in the 2008 and 2009, the 3D topological insulators has been proposed and also have been realized in the experiments. Continued, there are also very many examples on the topological superconductor, the wire semimetal, the topological crystalline insulator, Dirac semimetal, and so on. And this example, including the wire semimetal, Dirac semimetal, are the example for the topological semimetals. One of the most example for the topological material is the topological insulator. In topological insulator, the bulk is insulating. However, in the surface, the material can be conducting. Most interestingly, on the surface, the electron in different spin channels can move in different rows. Therefore, relatively low electronic resistance can be realized in the topological insulators. And this figure shows the observation in experiments of the electronic surface states in the topological insulators. Very interesting topological insulators can be applied in many fields, such as the topological insulators can be applied in the electronics, such as in the quantum computing. And also topological can be used in the energy field, used as the air battery electrodes. And also topological insulator can be also used as in the chemical industry. Besides topological insulators, there are also exist topological semimetals. Different from the topological insulators, the bulk state is not isolated, but have the definite surface state. This is called as topological semimetals. Topological semimetals contain many interesting properties, such as the massless bulk conducting electrodes, the abnormal charity, very interesting the Fermi arcs, and the surface superconduction, and also special photoconduction, magnetic breakdown, and so on. There are many typical topological semimetals. The most typical ones are for the Dirac semimetals and the wire semimetals. For Dirac semimetals, it contains the fourfold degenerated Dirac point. However, for the wire point, it only has a doubly degenerated nodal point. The proposal of the wire semimetals can be traced back to the 2011. In fact, topological semimetals can be classified into different categories. For example, topological semimetals can be classified by the dimensionality of band crossings. These are three typical examples. These examples contain these three ones called as nodal point, nodal loop, nodal surface. And very interesting, these 3 points have different dimensions of band crossings. For the nodal point semimetals, the band crossing shows the nodal point, and for nodal loop semimetals, the band crossing shows the nodal loop. And this is also the same for the nodal surface semimetals. In addition, topological semimetals can also be classified by the slope of the bands. Typically, for example, for the wire semimetals, it can be classified into the type 1 and type 2 wire semimetals. For the nodalized semimetals, it not only has the type 1 nodal loop and type 2 nodal loop, it also has the third possibility called as the hybrid nodal loop, and this will be discussed later. Different topological semimetals can show very different physical properties. Now, we come to our work on the designing of topological materials. First, I will introduce several nodalized semimetals in non-magnetic systems. This is the first family of our proposal. This family material called as the MB2, and this family of material contains this 7 materials. This material have the hexagonal crystal structures, and these 2 pictures are for the crystal structure for this family of the materials. In the following, I will make my proposal by using this material as the example. This figure shows the band structure for this material. In the band structure, we can observe 3 band crossing points near the form level. This 3 crossing points we terminate as P1, P2, and Q, as shown in this figure. Our further study found the band crossing P1 and P2 are not isolated. but reside on a nodal loop. And this figure shows the 3D band plotting for the P1 and P2. We can find it has formed the closed nodal loop around the key or around the key point in the Boolean zoo. Very interesting. Unlike former nodal loops formed by the two bands, we find that this nodal loop is very interesting because it forms by because it is formed by the band crossing among four bands. So this work is the first proposal of the nodal loops formed by four bands. More interestingly, we find that these four bands nodal loops can show very interesting Dirac surface states. This figure shows the surface the surface Dirac cones, and this work have been published in the Physics Review B. For another band crossing, we find that this band crossing is in fact a triply degenerated nodal point. We can see this figure. We can find the crossing is same to formed by the crossing among between two bands. However, we find the band for the E1 stage is doubly degenerate, and the other band thought as the A1 is a single edge. So this band crossing point is in fact the triply degenerate nodal point. We can find the triply degeneracy of the nodal point in this figure. We can find the nodal point is in fact crossed by the cross among three bands. Further, we find that this triply degenerate nodal point can have a topological transformation under the spin orbital coupling. We can find it can transform from a triply degenerate nodal point into the Dirac point. It's worth pointing out that our work has been followed by several other works, and these works have been focused on the material we propose, which is the TIP2. Moreover, our work has been cited for many times since its publication, and it has been a highly cited paper. I will introduce our another works. Previous works on the nodal lines are mostly focused on the type 1. In this work, we propose several type 2 nodal lines. These are the two typical examples. The first example shown in this figure, we can find it shows a band crossing as the type 2. And the band crossing for the nodal lines form the nodal lines in the Boolean zoo. Very interesting. For another example, we find that this material shows very interesting type 2 band crossings. It can show the drum head surface stage. In this work, we propose the first example of the type 2 nodal lines. And also, the proposal of the type 2 nodal lines for this material have been realized in the experiments later in the 2019. In fact, besides the type 1 and type 2, there's also the third possibility. This figure shows the typical type 1 and type 2. For nodal line, which formed only by the type 1 band crossing, is a type 2 is a type 1 nodal line. When the band crossing forms the type 2 band crossing, and this band crossing reside on the nodal line, and this is a type 2 nodal line. In fact, in the nodal line, it can have the third possibility. That is, in one nodal line, in a single nodal line, the band crossing can also have the type 1 and type 2. And in this work, we make the first proposal of the hybrid nodal line. We call such nodal line as the hybrid nodal line. And in this work, we propose the model for the hybrid nodal and tell us what the information for the formation of the hybrid nodal. Moreover, we found the first material for the hybrid nodal, and for this material, this figure shows the crystal structure of the material. We can find it shows several band crossings near the film level. Especially we observe the band crossing for the A1 and A2. And this figure shows the enlarged band structure for the A1 and A2. We can find the band crossing for the A1 is a type 1 band crossing. However, for the band crossing of the A2 is in fact a type 2 band crossing. And these two band crossings are not isolated, but reside on a nodal loop. And this figure shows the nodal loop. These four nodal loops are formed by this band crossing. That is to say, in the single nodal loop, it can show the type 1 band crossing and also the type 2 band crossing. This is a typical hybrid nodal loop, and this is the first material for the realization of the hybrid nodal loop. More interestingly, we find the hybrid nodal show very interesting magneto response, such as the unconventional magneto response, but including the current turning and also magnetic breakdown. These figures are very different with the typical type 1 nodal and the type 2 nodal, and this is only for the properties of the hybrid nodal. In nodal materials, an issue exists for a long time. What's the issue? The nodal is the nodals will be typically gapped by the semi-orbital coupling. We can see this figure. Without considering the semi-orbital coupling, we can find these are the band crossings, and the band crossing form the nodals. However, when we include the semi-orbital coupling, we find the nodal will open a gap. Obviously, this gap is not what we want. So, whether can we find nodal immune from this semi-orbital coupling induced gaps? In this work, we propose the theory for the topological nodal electrons. This figure is for the electron. The electron has the outside electrons which are floating on the walls of the lattice. The topological nodal electrons contain both features of the nodal and the electrons. And then in the topological nodal electrons, the material will immune from the semi-orbital coupling gaps. Then can we realize the topological nodal electrons? I will show in this work. In this work, we show the material realization of the topological nodal electrons in these nanomaterials formed by the second group and the fifth group. And this figure is for the crystal structure for these materials. And this figure shows the electronic band structure for the material. We can observe that near the Fermi energy, there exists two band crossings, namely band crossing A and band crossing B. We can find the band crossings reside on a nodal loop, and this nodal loop is formed by the excess electrons. So this material is a typical topological electron. In the final, I will talk about our design on the topological material for some examples of the magnetic topological materials. We all know that the magnetism is another important topic in the material science and condensed matter. And this figure shows the typical band for the material under different magnetic states. The first one is a non-magnetic metal. The second one is a magnetic metal. However, the third one is very interesting. In one spin channel, for example, in this figure, in the spin up channel is metallic. However, in the spin down channel is insulating. Such material is called as the half metal. The half metal have the most remarkable features of the 100% of the spin polarization. The half metals can have many applications, such as the spin injection in the conductivity, and also the JMR effect. Then, when question naturally comes, can we realize the magnetic topological materials? If the magnetic topological material can be realized, it will have many applications, especially in the topological spintonics. In our this work, we answer the above question. We can find it's very possible to realize magnetic topological materials. This figure shows the crystal structure for the material, and these figures are for the electronic band structures. We can find in the band structures in the spin up channel is metallic. However, in the spin down channel, it has a large gap above 4 eV and is in fact insulating. So this material is only conductive in the spin up channel, is a typical half metal. Apparently, we can observe in the spin up channel there exists many band crossings in the Fermi level. Our further study found this band crossing looks very like the hourglass. This figure shows the hourglass. We can find this band crossing where it looks very like the hourglass. Our further study found this hourglass points are not isolated, but reside on these nodal loops. These are the 3 typical nodal loops, and in the 3D Blink zoom, these nodal loops can form the hourglass networks. Very interesting, this hourglass network has the 100% of the spin polarization. For another example, in this material, we realize another topological half metal. This shows the crystal structure for this material. It has a hexagonal crystal structure, and this figure shows the band structure. Very interestingly, we find that this material is insulating in the spin up channel. However, is conducting in the spin down channel. In other words, this material is a typical half metal. This figure shows the band crossing in the spin down channel. We can find that this band crossing is typically formed by 3 bands. This is the first one, this is the second one, and this is the third one. And in another word, this band crossing is in fact a AAA degenerate nodal point. This is the 3D plotting for the AAA degenerate nodal point. Very interesting, we found this material can show very interesting topological transition and spin orbital coupling. You can find under spin orbital coupling, the AAA degenerate nodal point can split into 2 wire points, which is shown as the W1 and the W2 in this figure. You can find that these wire points are very interesting. Each has the it has such configuration is very different with the typical type 1 wire pond and the type 2 wire pond. And in this work, this is the first proposal of the type 3 Dirac wire ponds with the 100% of semipolarization. This one is the last example. Is realized in a 2D material, and this figure shows the crystal structure for this material is it has a tetragonal crystal structure, and this figure shows the band structure for this material. We can find in the spin up channel is metallic, however, in the spin down channel is insulating. So this material is also a typical half metal. We observe the band crossing in the spin up channel. We term them as the P1 and the P2. We can find P1 is a typical type 2 band crossing. However, P2 is a typical type 2 band crossing. Moreover, this 2 band crossing can reside on a typical node line and show in this figure. We can find in this node line it shows both the type 1 node point and also the type 2 node point. This is a typical hybrid node line. And this is the first example for the fully spin polarized hybrid node line. More interesting, we find this material can show very interesting topological phase transitions. For example, in different magnetization directions, it can show the hybrid node loop, so type 1 wire semimetal, type 2 wire semimetals, and so on. This is the summary for the work. In this talk, I introduced some of our works on the topological semimetals, including several non-magnetic node line semimetals, including these examples. And also, we also propose several topological half metals, and this topological half metal have 100% of spin polarization. And this is the acknowledgments. This work have these collaborators, including the Professor Sheng Yuanyang from the SUTD, Professor Yu Guiyao, Yu Zhiming from the Beijing University of Technology, and also the Professor Sheng Xialei from the Beihang University. Also, my colleagues in Hebei University of Technology, including Guo Dongliu and Ying Liu, and also thanks my my students, including the Jin Lei, He Qinli, and Wei Zhenmeng. Okay, that's all for my talk. Thank you.